behaves in a way your brain is not built to understand. Two perfectly good clocks can meet again and disagree about how much time passed, and we can measure that disagreement. Most of us carry an idea that feels too basic to question. Time is a single river. It flows the same for everyone. Your watch and my watch might be badly made, but if we fix them, they should agree, because time itself is universal. That belief is so deep that we treat it like a law of nature. But modern physics treats it as a useful approximation, the way the Earth is flat is a useful approximation for building a house. And here's the uncomfortable part. Relativity doesn't say your clock is wrong. It says your clock is doing exactly what time does along your path through space-time. Physicists have a name for that: proper time, the time measured by a clock that travels with you. You don't get to vote on it, you carry it. Imagine a simple scene. Two colleagues, call them Alex and Mara, synchronize their watches in a lab. Then, Mara goes on a fast trip and returns. Alex stays home. When they meet again, classical intuition says both watches should match because they started synchronized and ended together. Relativity says not necessarily. Not because math gets weird, not because reality is mystical, but because the rules that connect space and time are different than your intuition expects. In special relativity, the key ingredient is that the speed of light is the same in all inertial frames, a fact built into the structure of the theory and supported by enormous experimental evidence in modern physics practice and metrology. Once you accept that, the rest is not a taste preference, it's a logical consequence. Special relativity gives a clean relationship between speed and time dilation through the Lorentz factor. Gamma equals 1 minus v squared over c squared square root. You don't need to grind through the algebra to feel what it means. If something moves at speed v relative to you, and you compare clocks, you find that the moving clock accumulates less proper time between the same pair of meetings than a clock that stayed in your frame. MIT's relativity lecture notes show this through a simple light pulse clock thought experiment. If light must travel at speed c in every frame, then the moving clock's light has to trace a longer diagonal path while still moving at c. Longer path at same speed means more time in your frame, so the moving clock appears to tick slower. That's not a metaphor, it's geometry. And crucially, it's not about being tricked by perspective, it's about the measured time between physical events. Now for one of the cleanest reality checks. Muons are unstable particles created high in Earth's atmosphere. Their mean lifetime at rest is around microseconds. If you do a naive distance equals speed times time calculation, it looks like they shouldn't make it to sea level in large numbers. But they do. They're measured at sea level abundantly enough that this became a classic educational example and a historic experiment site. APS documents the early 1960s experiments, Frisch and Smith, performed at Mount Washington Observatory, comparing muon detection rates at altitude and near sea level. These experiments confirmed, within their uncertainties, that the observed lifetime of fast muons is extended in accord with special relativity. That's the key emotional jolt. Time dilation is not a philosophical idea, it's not a word game, it's how long real particles last before decaying, measured with detectors. If you want an even harsher version, CERN-related work measured relativistic muons in a storage ring. In the 1977 Nature paper, muons circulating with Lorentz factor gamma, approximately 29.33, were measured to have lifetimes around 64.4 microseconds in the lab frame, roughly 29 times longer than the rest lifetime. matching the special relativity prediction to the 10 to the minus 3 level. You don't get to explain that away by saying it's just coordinates. The muons don't care about coordinates. They decay when they decay. Your intuition was trained at speeds far below c. In everyday life, even a jet aircraft is crawling compared to light, so the time dilation factor differs from 1 by a tiny amount. Your nervous system has never needed to model it. Also, your brain assumes. Simultaneity is universal. Everyone shares the same now. Time is separate from space. Time is a background stage, and clocks reveal that universal time. Relativity breaks those assumptions, not with drama, with consistency. Special relativity forces you to accept that space and time are part of one geometry, and that the distance through space-time, your proper time, depends on your path. The MIT nodes show how time and space coordinates mix under the Lorentz transformation. Different inertial observers slice space-time into space and time differently, while still agreeing on measurable outcomes. Now we add gravity. General relativity says gravity is not just a force in space, it's related to the geometry of space-time. One of the direct, testable consequences is gravitational time dilation. Clocks deeper in a gravitational potential tick slower relative to clocks higher up. This isn't just astronomical, it's measurable in a lab. NIST described a 2010 experiment comparing two ultra-precise optical clocks and measuring the effect of gravity on time over a height difference of 33 centimeters, about 1 foot. Their summary even translates it into human language. Over a lifetime, the effect is tiny, tens of nanoseconds, but real and measurable with modern clocks. This is the moment the idea becomes hard to dismiss. Time is not only affected by extreme environments, it's affected by standing up. And NIST and GILA later pushed the scale down again. In 2022, they reported measuring the gravitational redshift across a sample separated by roughly a millimeter, with an implied fractional shift on the order of 10 to the negative 19, consistent with general relativity. A millimeter, that's not a black hole, that's a pencil tip. Here's the core message of this video. Time dilation is not saying time itself is an illusion, it's saying something stricter. The rate at which physical processes unfold depends on motion and gravity. Atomic clocks make this concrete because their ticks are tied to atomic transitions, reproducible, countable physical cycles. NIST explains how primary standards like cesium fountain clocks realize the SI second using the cesium hyperfine transition frequency 9,292,631,770 Hz and achieve extraordinarily low uncertainties, approaching 10 to the minus 16th in fractional frequency for the best microwave standards, with optical clocks reaching even beyond that in modern work. So when you see a clock shift, you are seeing the pace of a physical oscillator shift. That's why the "it's just math" objection fails. The math is a model, but the clock behavior is observed. Let's keep it conceptual. For speeds much smaller than c, special relativistic time dilation can be approximated as a tiny fractional change proportional to v squared over c squared. That's why everyday speeds don't matter much. For gravity near Earth, gravitational time dilation between two heights is related to the difference in gravitational potential. Near the surface, the effect per height is small, but with modern clocks, small is no longer undetectable. NIST's 2010 public summary gives a human-scale translation. A height difference of about a foot corresponds to a lifetime difference on the order of tens of nanoseconds over 79 years. tiny for people, but measurable for optical clocks. That's the point. Physics is not waiting for your senses to catch up. The unsettling implication is that the universe doesn't run on one master clock. It runs on local clocks, each tracing its own proper time through space-time. NASA explains gravitational redshift in a way that connects directly to everyday technology. Clocks under stronger gravity run slower than clocks viewed from weaker gravity, and timing differences matter for navigation systems like GPS. You don't need to quote exact microseconds per day to make the honest point. Satellite navigation depends on relativistic time corrections. If engineers ignore relativity, errors accumulate. NASA NTRS documents like Ashby's Parkes overview quantify the scale of orbital relativistic effects. Second-order Doppler, time dilation, and gravitational frequency shifts in low Earth orbit are around the 10 to the minus 10th to 10 to the minus 11th fractional level, exactly the kind of thing precision timing missions must model and measure. Because your brain evolved for low speeds, weak gravitational gradients, and short lifetimes. Most importantly, your perception stitches the world into a single shared now because it's useful socially and biologically. Relativity says the now you feel is not a property of the universe. It's a property of your experience. Physics replaces that with something calmer, a set of events in space-time and the proper time along world lines. That's not cold. It's just less anthropocentric. Physicists don't start by asking what feels intuitive. They start by asking what is operationally measurable. Time dilation is an operational claim. Synchronize clocks, separate them, reunite them, compare. Nuance, measure decay rates at different altitudes and energies. Atomic clocks, compare frequencies at different heights and velocities. If the clocks disagree in a predictable way, and they do, then time is not a universal background quantity. It's a physical quantity tied to motion and gravity. So when you hear time slows down, try not to picture a mystical, thick syrup. Picture something quieter. Two paths through space-time, two clocks that are both honest, a meeting at the end where the universe refuses to let them agree. And then remember the part that matters most. This is not science fiction. It is measured in particle lifetimes in the atmosphere and in storage rings. It is measured in optical clocks separated by a foot and even by a millimeter. Time dilation is not a weird math trick. It's the cost of living in a universe where the speed of light is fixed and where gravity is not just down, but part of how time itself is arranged. If you want, I can write a follow-up episode that stays equally grounded. Why now isn't universal, and what clocks actually measure. No hype, just the clearest path through the evidence. Soft CTA. If this helped you see time more clearly, consider subscribing.